Hello everyone, my name is Yapeng Jiang, and I'm from Sun Yat-sen University. Today, I'm honored to present our paper titled Obscura, Concealing Recomputation Overhead in Training of Large Language Models with Bubble Filling Pipeline Transformation. Our team is from Sun Yat-sen University, Hong Kong University of Science and Technology, Huawei Technologies, and the Peng Laboratory. This work explores how to reduce recomputation overhead in pipeline training by transforming and utilizing Bubble more effectively. A new AI paradigm powered by large language models has recently emerged, delivering strong performance across domains. As model and dataset size grow, memory demands exceed single GPU limits. To cope this, multi-GPU pipeline parallelism has become standard with, for example, the data parallelism, tensor parallelism, and the pipeline parallelism. With pipeline parallelism standing out for its low communication overhead and ability to scale to larger models. The one F1B schedule, namely the one forward and one backward pipeline, is a widely adopted schedule in the pipeline parallelism, as shown in this figure. It consists of three phases: warm-up, steady, and ending. The memory usage peaks at the end of warm-up phase. Additionally, we define two types of bubbles. The forward bubbles shows in diagonal blocks, which appear between the last forward and first backward pass. And the backward bubbles shows in crossed line blocks, which span from the first to the last backward pass. However, the 1F1B pipeline suffers from memory bottleneck in its early stages. Specifically, stage S out of P stage must retain activations for up to P minus S microbatches, leading to higher memory usage in earlier stages. As shown in our experiments, when scaling the model from 13 billion to 18 billion, stage 0 and 1 hit the memory limit first, while later stage in pipeline remain unaffected. A straightforward way to reduce activation memory footprints is recomputation, which discards activation during the forward passes and recomputes them during the backward passes. However, this comes with significantly computation overhead. The table above shows the memory and computation cost under different recomputation strategies, revealing a clear trade-off. Saving more memory inevitably incurs higher computation overhead. We integrate the recomputation into pipeline by applying it to stages with memory bottlenecks only. Approach we termed on-demand recomputation. This yields the following observations. First, compare the two all-stage recomputation. On-demand recomputation, where we apply recomputation only to stage 0 and stage 1, achieves better performance. To investigate the benefits of on-demand recomputation, we get the second observation. Backward bubbles can conceal recomputation overhead, as illustrated in the figure. After applying recomputation, the backward bubbles in the stage 1 are largely filled by the time extension caused by the recomputation of macro batch 6, preventing it from impacting subsequent executions. A similar effect is observed in stage 0. Although backward bubbles can partially handle recomputation overhead, their limited duration allows them to cover only a small portion of it. To explore further opportunities, we make a third observation. Forward bubbles are unutilized, as shown in the figure. Even after applying recomputation, forward bubbles remaining unused in the recomputation stages. Built on all 3 key observations, we propose a strawman pipeline derived from the 1F1B schedule through a 2-step pipeline transformation. First, identify and recompute. We identify stages that exceed the memory limit, termed adjusted stages, and apply recomputation only to these stages. Second, migrate. We shift forward passes in the steady phase of adjusted stages leftward into forward bubbles as much as possible. This causes the forward bubbles to shift right and convert into backward bubbles. The bottom graph shows the strawman pipeline. Compared to the original pipeline, the recomputation overhead shows in gray lines is successfully handled by the newly created backward bubbles, further reducing execution time. Although the strawman pipeline improves train efficiency by better handling recomputation overhead, it still faces 3 performance challenges. First, how to fully utilize backward bubbles. For example, in stage 1, the red marked region shows a backward bubble that is only partially used. This occurs due to the tight dependencies between adjusted and non-adjusted stages, which limited backward bubbles from handling recomputation. Second, how to reduce extra memory usage. As shown in the stage 0, the number of forward passes in the warm-up phase increases from 3 to 7 due to the forward pass aggregation, which raises activation memory usage. Third, how to address computation balance. In the stage 2, we see many new idle bubbles. This imbalance is caused by on-demand recomputation, which increases the workload for adjusted stages while leaving others underutilized. To tackle these challenges, we propose the Obscura, a computationally efficient pipeline training system for large language models that uses pipeline transformation to better conceal recomputation overhead. Here is an overview of Obscura. It consists of 2 main modules, the Obscura planner and the Obscura runtime. The Obscura planner transforms the original 1F1B pipeline into the Obscura pipeline and generates a deployment configuration for use by the Obscura runtime. The Obscura runtime manages the distributed deployment and model training during the execution. The Obscura planner includes 4 key submodules that performs a complete pipeline transformation. The first submodule, pipeline transformation, it transform one F1B pipeline to the Stallman pipeline. The second submodule, dependency relaxation, which focuses on the first challenge. And the third swapping aware recomputation submodule, which tried to solve the second challenge. And the fourth partition adjustment module, which solved the third challenge. To address the first challenge, we propose dependency relaxation. We first start by analyzing the computations and the bubbles in the Stallman pipeline. The left graph shows a simplified steady phase of two adjacent stages, one adjusted and one non-adjusted. Due to tight data dependencies, backward passes cannot shift left and forward passes cannot shift right, limiting bubble reuse. However, the opposite movements are allowed without violating interstage dependencies, as shown in the middle graph. This results in better utilization of backward bubbles, as seen in the right graph, leading to reduced execution time. Thus, we apply dependency relaxation to the Stallman pipeline in two steps. First, we shifted the remaining forward passes in the steady phase leftward, interleaving them with backward passes. Second, shift the backward passes rightward to fill the bubbles left by the forward aggregation. The bottom figure shows the resulting pipeline, where backward bubbles are further utilized, improving overall training efficiency. To address the second challenge, we propose a swapping-aware recomputation. We integrate activation swapping into the Obscura pipeline and introduce a swapping scheme with three phases: the eviction, loading, and the loading. In general, the eviction phase continues off-flows activations of macro batches to reduce peak memory usage during the warm-up phase. The eviction, loading, and loading phase bring back these activations for the backward passes. Let mu be the number of forward passes in the warm-up phases of our adjusted stages, and lambda be the number of activation blocks evicted. With swapping, the peak memory reduces from mu to mu minus lambda. However, swapping introduces communication overhead. If we recompute more and swap less, computation becomes the bottleneck. If we recompute less and swap more, communication cost increases. To balance this trade-off, we propose a swapping-aware recomputation technique. We modeled the execution time and the memory usage of Obscura pipeline, as shown in the left equation, where the red terms correspond to recomputation overhead and green ones to communication cost. The K represents the last adjusted stage. We also model recomputation strategies at the background using binary array to indicate whether each operator is recomputed. Finally, we formulate an optimization problem shown in the right equation to minimize the execution time of stage 0 while satisfying memory and bandwidth constraints. To address the third challenge, we propose partition adjustment. Since different stages may require different numbers of layers to balance computation, we first model uneven stage partitioning, as shown in the left equation. Here, The upper C denotes the total computation time per macrobatch for the slowest adjusted or non-adjusted stages. And A_S represents the activation size per macrobatch in each stage. We substitute this into our previous formula to estimate execution time and memory usage. Next, we introduce a partition adjustment algorithm that greatly transfers layers from the slowest adjusted stage to the fastest non-adjusted stage, aiming to balance computation across stages as much as possible. Now let's move on to the evaluation. Our experiments were conducted on NVIDIA A100 80GB GPUs using the DeepSpeed framework. We evaluated the Llama-2 and the GPT-3 models with varying sizes. We compared against the 5 baselines. The first 4 are from framework. The double show indicates the state-of-art 1F1B pipeline schedule with even stage partition. The double plus means the full recomputation strategy is applied to all stages based on the 1F1B pipeline. And OHP-CMB. This work apply the recomputation strategies proposed in the first work that drops activations of specific operators, including norm activation and element multiplication. And the B-pipe, it eliminates the memory bottleneck by transferring activations from early stages to later ones using an activation balance method. And the fifth is our own domain pipeline. Throughput is used as the primary evaluation metric. First and foremost, regarding end-to-end throughput across different models, batch sizes, and mode scales, Obscura consistently delivers leading performance compared to other methods. Specifically, Obscura achieves speeds ups of 29 to 31% for the 18 billion and 23 billion models, 22 to 27% for the 28 model, and 22% speed up in the extremely case of a global batch size of 64 for the 28 model. About the memory usage, Obscura achieves better memory efficiency than double and OHP-CMB, reaching a memory balance comparable to B-pipe. In addition, we analyze computation time and bubble time, showing that the Obscura effectively utilize pipeline bubbles. With the integration of swapping, it adopts a cost-efficient recomputation strategy, resulting in short computation time than double plus. We also conducted experiments to analyze the performance impact of each module within Obscura. To conclude, we propose Obscura, a computationally efficient pipeline training system for large language models that leverages pipeline transformation to better conceal recomputation overhead. Thank you. Thank you for listening to our work. Thanks.